In this video, we're going to prove this beautiful inequality that if n is a positive integer, the sum of 1 plus 1 over 2 cubed plus 1 over 3 cubed all the way up to 1 over n cubed is less than 3 halves for all n. So it doesn't matter how many terms you add, you're always going to be less than 3 halves. And it's going to be a beautiful proof because we're going to actually train with how to think and how to construct mathematical induction proofs that are not very obvious. Okay, so it's a little bit of an insightful one. So let's just dive into it, and don't forget to smash that like button and subscribe for more fun math content. So we're going to actually try to understand how this works. Now, the first thing I want to tell you is that applying induction directly may not work. Okay, so if we just say that our induction proposition P of n, right, we're trying to prove that P of 1 is true, it's true for n equals 1, and then P of n implies P of n plus 1. If our induction proposition is literally this statement that 1 plus 1 over 2 cubed all the way up to 1 over n cubed is less than 3 halves, then if we want to derive from that the next step of the induction, which is the n plus first statement, right? We're doing it step by step. If we want to show this is true, well, it's not going to work, because to take this sum and get P of n plus 1, we're basically saying the same sum plus 1 over n plus 1 cubed, right? And how do we know that even if we just know this is less than 3 halves, it could be any number less than 3 halves? And it's possible that if it's very close to 3 halves, adding an extra term like this would tip it over the edge and make it greater than 3 halves. Okay, so that cannot be our induction proposition. It has to be something stronger. That's the key insight. We're going to have to modify our induction hypotheses to something stronger where P of n will imply P of n plus 1. And that stronger thing is that this term has to depend on n as well. Okay, so whatever it is, it should not be 3 halves. It should be 3 halves subtract something that depends on n. And then using that, what we can do is we can then sort of say adding on another term depending on n will be a new statement in the induction, and that would be true. Okay, so what term should we pick? Now, I'm not going to backtrack and tell you I'm going to talk you through my thinking process as we go along, but I'm going to backtrack it right now. I'm just going to tell you what the statement should be. And the statement is going to be 3 halves minus 1 over 3n. Okay? So why is this? Okay, so what's the idea? So as I said, when we take this statement P of n plus 1, our new induction proposition is going to be 3 halves minus 1 over 3n plus 1. Okay, so that's something that could potentially be true, because this term has, the right hand side has also increased as n has increased. Okay, so that's our statement, and we have to now do a proof by mathematical induction. So I'm going to get into that. And another thing that really helps the channel is there's a hype button for many people who watch the channel. It's a hype feature. If you click the hype button just below the video, it helps disseminate new channels or smaller channels to keep growing. All right, so hope you're enjoying this proof, and let's just jump right into the next step. So we're now going to do a proof by mathematical induction. P of 1. Okay, so again, you're going to wonder how I got the 3n, right? So I'm going to dissect that step by step. P of 1 is just going to be the statement where the left-hand side is just 1. You're adding one term of the sequence. And the right-hand side is going to be 3 halves minus 1/3. Okay, so it's going to be 3 halves minus 1/3. And that's why I put a 3n and not just an n, okay? Because, it makes sense. You're subtracting off 1 over n, for example, because as n gets larger and larger, this is going to approach 3 halves, okay? 3 halves minus 1 over n. But the reason I put a 3 is because then if I didn't have a 3, I'd have 3 halves minus 1 on the right-hand side, which would not be greater than 1. So this makes sure the base case of the induction is satisfied, which is very important to check always. Don't forget that. 3 halves minus 1/3 is easy enough to do. It's just going to equal to 7 over 6. So basically that inequality is true. Now for induction, okay, we've shown P of 1. We want a principle that says that assume P of n is true, right? Assume P of n, and then we want to prove that P of n plus 1 is true. Okay, prove P of n plus 1. That's what we want to do. Okay, so then we've proven for all n, because P of 1 will then imply P of 2 using this statement, and then P of 2 will imply P of 3 again using this statement. So we need a mechanism. We need to show that P of n implies P of n plus 1. If P of n is true, P of n plus 1 is true. Now basically what you want to do is you want to say that P of n is true is this inequality. Now for P of n plus 1 to be true, we're adding something to the left-hand side, we're adding something to the right-hand side. If we know the thing we're adding to the left-hand side is less than the thing we're adding to the right-hand side, then P of n will imply P of n plus 1. Makes sense, right? So the left-hand side, we're adding 1 over n plus 1 cubed. Okay, so we want what we're adding to the left-hand side, which is 1 over n plus 1 cubed, to be less than what we're adding to the right-hand side. What are we adding to the right-hand side? We're going from this number to this number. So to do that, we have to add 1 over 3n to cancel that off, and then subtract 1 over 3n plus 1. So the thing we're adding to the right-hand side to go from this to this is we're going to be adding 1 over 3n minus 1 over 3n plus 1. And now the inequality we want to verify for all n at least 1 is this inequality. Okay, then we have shown that P of n implies P of n plus 1. And watch till the end, because I'm going to show you some beautiful sort of math around this sum as well. I'm going to talk about that a little bit. It's very, very famous actually. And now, so what we're going to do is we have to show this is true. So for this, we'll just simplify the right-hand side, right? The right-hand side, by making a common denominator is going to be 3n plus 1 minus 3n divided by the product of the denominators, which is 9n times n plus 1. Okay, so 9n times n plus 1. And again, that's going to equal to, well, 3n plus 1 minus 3n is just going to be 3. Okay, it's 3n plus 3 minus 3n, so it's 3 over 9n times n plus 1, and that's just going to equal to 1 over 3n n plus 1. Okay, 1 over 3n times n plus 1, and so that's pretty cool. And the left-hand side is, of course, 1 over n plus 1 cubed. Okay, so we want to show that 1 over n plus 1 cubed, we want to show that that is going to be less than that, right? That's what we want to show. So we've got that. Now we're just going to manipulate the inequality to see why this should be true. I'm just going to do it that side of the board. All right, so saying that this inequality is true is by cross multiplying. It's the same as saying that 3n n plus 1 is less than n plus 1 cubed, okay? So here's an important thing again that I'm doing is these are all logical equivalences, okay? So basically, I'm backtracking, but I'm basically going to get to a true statement. Generally, if you want to do a proof very cleanly, you'll start with the obviously true statement and then get to this inequality, but I'm using logical equivalences to say, okay, 1 over n plus 1 cubed less than 1 over 3n n plus 1 is equivalent to saying 3n n plus 1 is less than n plus 1 cubed, okay? Because these are all positive numbers, okay? So there's nothing, n's a positive integer. And now, of course, this is again the same as saying we can cancel off. We can make this a 2, and we can cancel this off. So that's the same as saying that 3n is less than n plus 1 squared. Okay, and of course that's the same as saying by subtracting 3n on both sides that 0 is less than n squared plus 2n plus 1 minus 3n, which of course is equal to n squared minus n plus 1. Okay, so sometimes these can be tricky to show. You may ask, how do I show this? In this case, there's a nice simple trick, is that basically n squared minus n plus 1, n squared minus n is n times n minus 1 plus 1. Okay, and so the point is this true? Now we just reduced to showing this is true. That will imply our induction step, P of n implies P of n plus 1. And of course this is true because if n is at least 1, this quantity here, n times n minus 1, is always going to be at least 0. Okay, if n is 1, it's literally going to be 0. But if n is at least 1, then it's going to be a positive number. It doesn't really matter because you're adding a 1. So this is at least 0, add a 1, it's going to be greater than 0. Okay, so that implies a statement, and that's the proof of this, okay, because our induction step was that, we've proven for all n this is less than 3 halves minus 1 over 3n. So in particular, it's going to be less than 3 halves for all n. And what is the fun sort of connection with this? All right, so the fun connection with this is that this sum, okay, this series, if you just add it on forever, if you take sum n equals 1 to infinity of 1 over n cubed, okay, so you add these terms forever and ever, actually, it's so beautiful. That's a famous series. It's called Apéry's constant. The value of this is called Apéry's constant. It's also known as the zeta function, the Riemann Zeta function evaluated at 3. And no one knows the exact value for this. There's no formula for this. It's kind of mind-blowing. It's a major open problem. It's never been solved. What's the exact value? Is it, can we find a formula for it? But it's approximately equal to 1.20 ... okay? So our bound is not that tight. This is 1.5. So here's a challenge for you. It may or may not be possible, but it's just to creatively play with math, just to sort of practice with this, just to experiment. Can you actually show 1.20 is less than 4/3? Can you maybe show that this is less than 4/3? Like, just as a challenge, can you create an induction proof experiment and see? And drop a comment down below. I'd love to see what you think. And I've got 2 fun videos for you. The first video is related to this infinite series. Instead of taking sum n equals 1 to infinity 1 over n cubed, you can take sum n equals 1 to infinity 1 over n squared. And that is a very famous sum that Euler discovered. He became famous for doing this. A 100-year-old problem. He discovered it around he was 28 or 29. Major open problem. He found it's equal to pi squared over 6. And his proof is so intuitive and simple using sine x, okay, using basic trig and understanding in a very creative way. Check it out. You're going to love that video. It's going to pop up on the screen here. Have an amazing day, and I'm super excited to catch you in either of these 2 videos.